last class we have discussed the solution of algebraic Riccati equation by using numerical reliable control algorithms. That algorithm is the Schur method. We could not complete this whole derivation of this one. So, we will just continue that one, and after that we will discuss the frequency domain interpretation of LQR control systems. So, if you recollect this one, our method is we have to solve the algebraic Riccati equation by using Schur method, which is numerically more reliable than any other iterative methods for solution of algebraic Riccati equation. So, this algorithm steps, if we recollect this one, what we did it, first you form a Hamiltonian matrix with the knowledge of system matrices A, B and the performing index matrices, the state weighting matrix Q and R. So, we can form Hamiltonian matrix. Then with the help of what is called QR decomposition technique or algorithms, we convert HM into upper Schur form. What is upper Schur form? That we have converted HM with a transformation, that is with a transformation W, that so that W transpose HM W will convert into a new matrix S, okay, that S is having a special structure, and the structure of S is we have discussed that into this form S11, S12 dot S1 K, and we have a such block S11, S22 is a K block, and each block S11 or S22, S33 block will be either 1 by 1 block scalar quantity or 2 by 2 blocks, and remaining lower blocks or lower parts of this matrix is a 0, all these things. So, it is a upper triangular structure and each diagonal block either 1 by 1 or 2 by 2 matrices. So, this and how to convert this thing using that is QR decomposition method. We are discussing this one, that suppose any matrix A is given, then you assign a matrix A 0. So, you decompose this thing that Q 0 into R 0 matrix, and Q 0 is the orthogonal matrix, R 0 is upper triangular matrix. Then rewrite this equation that A 0, they reverse the order R 0 into Q 0, that is not equal to A 0. So, we are writing A 1 is equal to R 0 Q 0, which can be written is in place of R 0 I can write it Q 0 inverse A 0, and since Q 0 is a orthogonal matrix, that inverse is nothing but a Q 0 transpose. So, it is Q 0 transpose A 0 this, and that A 0, that now A 1 is decomposed, this A 1 is now decomposed Q 1 into R 1, that QR decomposition. Then rewrite in opposite or reverse order R 1 and Q 1, that will not be same is equal to A 1. So, A 2, and this R 1 value you put it from this equation. What is R 1? R 1 is nothing but a Q inverse A 1. So, I put the value of Q inverse A 1, Q inverse is orthogonal, Q 1 inverse is orthogonal matrix, Q 1 is orthogonal matrix. So, that transpose will be Q 1 transpose this one. So, if you proceed like this way, again we will get at kth iteration is like this way, Q 0 initial 0th iteration, Q 0 Q 1 Q 2 dot Q and Q k minus 1 whole transpose A 0 Q 0 Q 1 Q k minus 1. Since each is an orthogonal matrix Q 0 Q 1 Q 2 dot Q k minus 1, their product also orthogonal matrix. So, we have written that all products together is Q transpose and A 0, and now when it will stop this one, until unless it has converted into a that matrix A is converted into A k is converted into a upper triangular form. Not only upper triangular form, you have to that what is called A 1 1, that final menu A k 1 1, A k 2 2, A k 3 3. In this way, whatever the matrix will get it, each block will be either 1 by 1 matrix or 2 by 2 matrix, then we will stop it. So, this has converted into a upper Schur form. So, we have discussed up to this last class. Then we will see, that is our remark. It can be shown that by it can be shown that sequence of A k, that means A0, A1, A2 in this way, by using the QR decomposition technique in this way, sequence of A k converges to RSF reduced, R means reduced Schur form, converges to reduced Schur form. This is so. This we know this one, that if you do like this way, ultimately that A k will converge to the Schur form. So, just in short, the theorem we can write it now like this way. Let A is n cross n matrix, at a real matrix, let us call, comma, then there exist this symbol is there exist an n cross n orthogonal matrix, n cross n orthogonal matrix W, whose dimension is n in this, such that that S is equal to W transpose A W, and this W is n cross n. Agree? What is W? If you consider the earlier discussion, this W is nothing but a Q. What is Q? Q is a sequence of orthogonal transformation, what we made it QR decomposition Q0, Q1, Q2 dot dot Qk is Wk, this if you see. So, this is the way you can do it, where S is equal to S11, S12 dot dot S1k, S22 this is 0 dot dot S2k, and in this way last will be SKK. So, that dimension is n cross n. Agree? This dimension is n cross n. So, this is structure of S11, S22, SKK is are either 1 by 1 or 2 by 2 matrix, and it is upper triangular form. So, next is that what is our next step, our algorithm. First step is form a Hamiltonian matrix, then convert into a what is called, if you see the our second, that is our second step is, you with the help of QR decomposition you convert into Schur form. Agree? That Schur form we know how to do it, but before that you must know how to decompose a matrix into QR algorithm. Agree? Or using a what is called orthogonal transformation, or using a Householder transformation. Householder transformation is an orthogonal transformations. It is a special case of orthogonal transformation, Householder transformation. So, our step 3, step 2, that Hamiltonian matrix is converted into a reduced Schur form, and Hamiltonian matrix, you see the dimension of a Hamiltonian matrix is 2n cross 2n, n is the order of the systems, and this matrix contains a set of eigenvalues in the left half of the S plane and the set of eigenvalues in the right half of the S plane, and the eigenvalues in both S plane, number of eigenvalues in S plane and what is called S plane in the left hand half, and the number of poles in the S plane in the right hand plus number are in same. So, and they are mirror image of each other. So, now next step is the Schur form. The Schur form 2, that means, this is the our algorithm steps, if you look, this is the algorithm 1 and the equation number 1 and this is the equation number 2, let us call. This is the equation number that whatever we got is should form this blocks S11, S22, all these thing blocks are either 1 by 1 or 2 by 2, but their eigenvalues are may be stable or unstable throughout this block S11 to SKK. So, now we have to rearrange the eigenvalues. First we will make all the stable eigenvalues of S matrix first and remaining blocks will be the unstable eigenvalues of HM matrix, means Hamiltonian matrix. So, from the Schur form 2 is reordered with the help of some orthogonal matrix, let us call B, whose dimension is twice n into twice n, because H is a dimension of HM is a dimension 2 n cross 2 n, and with using the Householder transform some orthogonal transformation, we convert into a S. S is nothing but a W transpose HM into WM, and HM is twice n into twice n dimension and W is twice n into twice n. Again on S we are doing some transformation, orthogonal transformation, so that the S matrix is converted into a special form, means it will be upper triangular form, but only the all eigenvalues which are stable that will be put first and the unstable eigenvalues will be put next. So, this using this transformation matrix, if you do this one B transpose S V, this is dimension is 2. Ultimately reordering only is reordering of SR matrix, that S matrix can be done by using elementary row and column operations, that one can do it into reordering. So, let us call after reordering we got it that if it is a V transpose, then what is S? If you recollect, S is W HM W then V. So, you consider this is U. So, it is nothing but a U transpose HM U, and this U dimension is 2 cross twice cross as this. So, let us call this is equation number 3, and the structure of SR, if you see this structure of SR will be like this way, that SR 11 SR 12 dot dot SR 1 SR 1 K, then or okay, light it like this way, SR 11 SR 22. What does mean SR 11 block is, this is n cross, this is n cross n, and this is n rows and this is a n columns. So, SR 11 contains all the eigenvalues of stable eigenvalues of HM which are stable in SR block, means n cross n blocks it will consider, and SR 1 block is the upper triangular form, SR block in the upper triangular form. Each block of SR 11 is either 1 by 1 or 2 by 2 matrix, and all eigenvalues of L SR 11 are stable eigenvalues, and SR 2 SR 22 all eigenvalues of SR whose dimension is n cross n eigenvalues are unstable, but reverse sign with a stable eigenvalues of SR 11, is unstable eigenvalues. So, we from SR we converted into SR. So, from S we converted into SR by rearranging that one, so that first stable block n cross n contains the stable eigenvalues, and next n cross n block of this one diagonal block is considered the unstable eigenvalues of H m. So, that is this one. So, just I am writing it what is SR 11. SR 11 whose dimension is n cross n, again is upper triangular matrix and its diagonal block is either 1 or 2 block. Matrix with its eigenvalues are stable, means lambda I less than 0 for I is equal to 1 2 dot dot n, whereas SR 2 is unstable eigenvalues, of H m. Because how? Because we know the transformation, if you do the transformation, that we have got S W transpose S is a W transpose H m W. The eigenvalues of H m is same as the eigenvalues of S, or in other words you can say eigenvalues of S is same as the eigenvalues of H m, because this is the similarity transformation like this. Since we have done again on similarity transform some transformation on S, that is S r is equal to, we got it U transpose H m and U, that eigenvalues of S r is remain the same as eigenvalues of H m, where U is equal to, if you see this, we have written U is equal to W V this. So, once we have done this third step, we have converted into a what is called Schur form by reordering. Once again we have reordered only this, that is the only difference from the second step 2. Step 3 is different from step 2. We have reordered the matrix Schur form and in SR form, SR matrix, so that stable eigenvalues will come first and next is unstable eigenvalues. So, from this statement we can write it from equation 3. See the equation 3, that equation 3. So, if we multiply by this, if you multiply it by both side by u, then what will get it? This nothing but a H m u is equal to U S r, both side I multiplied by U. U is the orthogonal matrix. So, U transpose U or U transpose U into U transpose or U transpose into U is equal to identity matrix. So, this we can write it, that from 3, you can write it from 3. Then let us write the detailed structure of U. If you recollect, the U is a 2 n cross 2 n matrix. So, I am just putting into that 2 by 2 blocks, U 1 1, U I am writing U 1 2, U 2 1, U 2 2. This number of rows n, this number of columns n, the number of columns n, here the number of rows is n. So, you know all these things. Then U 1 1, U 1 2, U 2 1, U 2 2. Similarly, dimension, if you partition in this way, you can know this one. And S r dimension is what? S r 1 1, S r 1 2, S r 1 2, then 0, S r 2 2. Agree? This is the things. Now, you see I just multiply this into this form, then what we will get it, this dimension, this is 2 cross into 2 cross, agree. So, now if you multiply by this, then what we will write it, H m, I multiply by this block by H m. So, it is nothing but a u 1 u 2 1. Similarly, I have to multiply this matrix with this block is equal to, this block is u u 1 u 1 2, this multiplied by this multiplied by this multiplied by this. So, it is u 1 S R 1, then this multiplied by this multiplied by this multiplied by this plus this multiplied by this, it will be u 2 1 S. So, I can write u R 1 1 of this, both side this. So, this is this matrix is the stable eigenvalues of H m matrix, agree. So, now you see this one, the eigenvalues and eigenvector definition, the matrix A multiplied by each column. How many columns are there? N columns. How many rows are there? Twice n rows. So, each vector represents the eigenvector of the matrix H m corresponding to eigenvalues of S R 1 1. The first element S R 1 1 structure is what? Is the upper triangular structure. So, if you multiply it by this, then it will be coming that one. Just see this one. I multiplied by, there is how many columns are there? N columns are there. First column multiplied by H m. First column multiplied by H m is equal to that first column multiplied by S R. S R is structure is what? S R 1 1 structure is what? If you see, this is this 0 0 0 form, then this 0 0 0 form, and similarly this will be this form 0 0 0 form, and it is something like this structure. So, if you multiply it by this, then what you will get it, that each column corresponding to the, suppose first column, this first column of this one corresponding to eigenvalue of the matrix S R 1 of, this is the eigenvalues, this is another eigenvalues of this one, either 1 by 1 or 2 by 2 eigenvalues of the matrix this. So, this vector corresponding the eigenvectors corresponding to the stable eigenvalues of H m matrix. This is the eigenvectors of the matrix H m corresponding to the stable eigenvalues of H m, that this is the eigenvectors. So, you have partitioned this one and we have proved this one. With the knowledge of eigenvalues and eigenvector of the matrix, we can get the solution of algebraic Riccati equation. Once I know the eigenvectors of H m matrix, okay, then I can find out what is the solution of this one by using the method we have discussed in method 2. So, next step, so if you want to write it here, this is the eigenvectors corresponding to eigenvalues of S R 1 1 or the stable eigenvalues or the stable eigenvalues of H m, okay, stable eigenvalues of H m. So, now step 4 we can write is immediately we can write step 4, the solution of our Riccati equation. The solution of our algebraic Riccati equation, in other words, the A transpose P plus P A minus P B or inverse B transpose P plus Q is equal to 0, this is n cross n, is P U21 matrix multiplied by U11 whole inverse of that one. Now, see this one, this matrix, this vector you got it, the dimension of the vector is twice n cross n. So, first n rows you retrieve from the vectors, that is U11, and the remaining vectors of n cross n will be U21. So, you just complete like this way and you will get the solution of the Riccati equation. That what in step 3 is done, we have evaluated the eigenvectors of the matrix H m corresponding to the stable eigenvalues by QR decomposition techniques, which is numerically more reliable than what is called the our earlier simple eigenvalues eigenvector methods. So, we have used the different techniques to find out the eigenvector of the H m matrix corresponding to stable eigenvalues. Numerically reliable algorithm we have used it. So, one can solve this one instead of directly taking the inverse, I can do it like this way, that P U11 is equal to U21. This I can write it like this way, that this is unknown. So, since this we can solve it, the solve P using Gauss elimination method, just to avoid the inversion of this matrix. If it is a large dimensional problem, that one should avoid the inversion of this problem and solve it by Gauss elimination method. So, the advantage of this method is, if you see the advantage of this method, we can just tell the advantages of Schur method for solving ERE method, ERE equation. One advantage is there, the numerical hazard is not, will not face any numerical hazard. So, not suffer any numerical hazards while computing the eigenvectors associated with multiple eigenvalues of H m. 1. Second is significant speed is speed of solution of this Riccati equation, time required for solution of this Riccati equation is significantly improved compared to the any other iterative method. So, second step is significant speed in comparison with other iterative method, only disadvantage is computer storage requirement is high, because it requires 2 n cross 2 n. So, next is your computer storage requirement, disadvantage is the storage requirement. Of at least 2 n cross 2 n array. So, one can solve the solution of algebraic Riccati equation by Schur method, one can solve by iterative method, but the Schur method is numerically more reliable compared to the iterative method, because when you have a rather direct eigenvalue eigenvector, when you have a multiple eigenvalues are there, multiple eigenvalues there. So, we have to find out generalized eigenvectors of this one. So, this will create problem if you use the standard eigenvalue eigenvector method. So, this technique, that is QR decomposition technique, will avoid such type of problems when you have a multiple eigenvalues of a system matrix. Where okay. Next, we will go for what is called our frequency domain interpretation. We have designed the controller, that is LQR controller, and we have studied the LQR controller, that whether a minus b k of the closed loop system will be stable or not. We have seen the requirement is Q must be positive definite matrix and R positive semi definite matrix, R must be positive definite matrix. That suffice that the closed loop system is stable. And now, it and of course, this before that we have to see that A and B must be controllable, at least stabilizable, or A and Q must be detectable. This now frequency, now this controller what we have designed it, now one has to interpret the results more in depth or details in frequency domain. In the sense, in frequency domain you can say what is the phase margin and gain margin of the corresponding design controller, closed loop system design controller, what is the phase and gain margin of this one. So, that will investigate or you will study this one, that phase and gain margin of the LQR control systems. So, frequency domain interpretation. Frequency domain interpretation of LQR design control and LQR control system design problems. So, let us consider our plant dynamics x dot is equal to A x t plus B u of t, x of t is equal to x of 0 is the initial condition. So, our problem in and the corresponding performing index is j is equal to half 0 to infinity x transpose t, this is infinity x transpose t q x of t plus u transpose of t r u of t dt. So, our problem is given the system, you design a controller u of k t such that the performing index is minimized. Again, and the performing index, this is given the performing index is minimized. Then this problem statement is given the plant, you design or you can write design a controller u of t is equal to minus k of x t, assume all the states are available, design k of t such that the performing index is minimized. Agree? So, before that we have to make an assumption, that assumptions. One, A and B is controllable or at least stabilizable. 2, A and Q, Q is this is detectable, detectable. These two condition we have to check it. Once it is stable, then we are going for designing a controller U of k, and the k can be found out. K can be found out by solving the algebraic Riccati equation. Agree. Once you solve the algebraic Riccati equation, get the value of p, then your k is nothing but a you will see R inverse B transpose p, and this p is the solution of algebraic Riccati equation, that we know all these things. So, let us call this is the equation number 1, this is the equation number 1, this is the equation number 2, and using the control law in the given systems, then the optimal control law u is equal to u of t is equal to minus R inverse B transpose P into x t, and which is nothing but a x of k t. Agree? And P is the solution of Riccati equation, that where P is obtained from the solution of algebraic Riccati equation. Agree? This solution you will get it. So, this is, let us call this is equation number 3. This is the equation number 3. So, now what is the closed loop system equation? In system equation 1, you put u is equal to minus k x from 1, and using u is equal to minus k x, we get that x dot is equal to a minus b k x of t, and this is nothing but a closed loop systems. AC, this denoted by AC. Agree? So, this is, let us call equation number 4, and this is asymptotically stable, that we have proved it. This a minus b k is asymptotically stable, that we have proved earlier, this one, and its corresponding. So, the characteristics equation of the closed loop system, characteristics equation of the closed loop system is given by, what is the closed loop system characteristics equation? Determinant of, let us call it denoted by, this is the C is closed loop system, determinant of that our closed loop systems, determinant of S I minus our closed loop system A minus B k, this. So, let us call this is equation number 5. So, this is the nothing but a, if you take the determinant of this one, you will get a polynomial of order n is equal to 0. This is the characteristics equation. So, if you take the determinant of this one, you will get a polynomial in S of order n, because this dimension of this one is n cross n. So, now this we can write it, or determinant of S I minus A this plus B k of this is equal to 0, which you can write it into this form, I plus B k into S I minus A whole inverse, this whole bracket into S I minus A, same as this one. So, you push it S I minus A inside. So, this will be identity matrix B k S I minus A, this is bk, bk si minus a inverse si, it is identity matrix. So, it is bk and this will be si minus a. So, it will remain same that one. So, this I can write it now into this form, that you know this property is the determinant of that let us call f E and f. E is a matrix, f is a matrix with proper dimension is equal to determinant of E into determinant of f. So, that property I will use it here. Here one matrix, this is another matrix. So, you will write a determinant of S I minus A into determinant of I plus B k into S I minus A inverse of that one is equal to 0. Now, we just consider this, let us call this is equal to m and this b is equal to n. So, once again I can write it, the determinant of S I minus A is same as the determinant of S I minus is determinant of this is same as this plus k S I minus A whole inverse into B. So, order is reverse. So, this is the property of this one, determinant of 1 plus I plus m n is same as determinant of I plus n m. Agree? This we have written is here, that property we have used it. The reverse the order, this is I have considered m, this is n, I have just reversed the order. So, now we can write it, the determinant characteristics equation of the closed loop system characteristics equation is nothing but a determinant of this one and determinant of that one. We can write it in this form. Agree? So, let us see the two that controller what we have designed LQR controller in time domain representation. What is the block diagram? We have already seen it now. Now, we will see in frequency domain. Agree? Then what is your block diagram representation of this one in time domain. So, since it is a regulator problem, LQR is a regulator problem and reference input is 0, because it is this controller is designed, if there is any initial disturbance is there in the state, then regulator will take care of to bring the that state affected state to bring it in to its equilibrium position. Agree? So, the controller job is that one only. So, B, then this indicator, that output of x t, this is x dot of t, then this A, then this is your u t, and the controller is designed, this is R inverse B transpose P, this is nothing but a k controller gain k minus 1 and that is coming to here plus this plus. So, this is R is equal to R of t is equal to reference input is 0. This is a regulator problem, means that due to the initial state disturbance, the controller will bring the state to equilibrium position by minimizing a performance index, that is this. So, this is about the controller. If you see that part, this part is our plant, this is the plant and this part is our controller, this is the controller, then output of this controller is u t and this figure, if you see more carefully, it is a LQR based control systems, and it is represented in time domain. Agree? It is represented in time domain. Now, let us see in the frequency domain representation of that LQR control systems. Agree? Frequency equivalent representation in frequency domain. The equivalent representation in S domain or frequency domain, or you can say frequency domain. So, look at this expression, this is nothing but a, this block nothing but a representation is x dot is equal to A x plus B u. So, that is nothing but A x dot is equal to A x plus B u time domain. And what is the frequency domain representation of that one? S I minus, take both side Laplace transform, assuming that initial condition is 0, then this is a x of this is equal to B u of s, that one. So, that I am now representing this one. So, x of s. So, S I minus A whole inverse into B, this output is x of s. So, this is the input, u is the input, and this is the output x of s. So, output is this, input is this u of s, that output. Then this is going to the controller in S domain. Our controller is R inverse B transpose P, then multiplied by minus 1, and that will come to here, that is our u of s, and this is R is R of s is equal to 0. Now, say this is our representation in S domain, that this figure is that your LQR based control system bracket in frequency domain. So, this is our case. If you see, this is our controller. Once again, if you want to equivalent to this one, this is our controller. This is our controller, and controller how it is related US is equal to nothing but a, that minus this corresponding to k is a constant matrix multiplied by our input is x of s. This is the input, and this is the output from the controller. US is the output from the controller, and x is the output of the plant, input to the plant is US. So, this is our controller, and this is our plant. So, this is now. So, let us see this one, that now what we are doing it here, adding and subtracting, P into S. P is the our that solution of the Riccati equation, that P, S is the S domain S, that frequency domain. Agree? 2, 3 means equation 3. See this equation number 3 of that one. So, equation 3 is our algebraic Riccati equation. With this equation, we are adding P into S and subtracting. So, the resultant expression will remain unchanged. So, if you do this one, P, then S I minus A plus P s, I am adding the minus P s minus, sorry, so minus, so minus S I minus A into P, agree, plus P B R inverse B transpose P minus Q is equal to 0 null cross n. What I did it, if more specifically, first that algebraic Riccati equation, equation number 3 I multiplied by minus 1, and then I have added P s, subtracted P s, and by manipulating we got it like this way. So, let us call this is equation number, we have gone up to equation number I think 5, this is the last equation is 5, agree. So, we can see the this is equation number 6. So, this we can write it, if you take q is right hand side, I can write it that P S I minus A plus S I minus A P plus P B R inverse B transpose P is equal to Q, agree. So, now I both side I multiplied by pre-multiply by that B transpose minus S I minus A whole inverse and post multiply by S I minus A inverse B. So, this equation I pre-multiplied by B transpose S I minus A inverse and post multiplied by that one. So, if you pre-multiply and post multiplied by that one, then what will this come S minus, that is B transpose. So, B transpose minus S I minus A whole inverse P into that expression I am writing now. So, S I minus A plus minus S I minus A P plus P B R inverse B transpose P, then this multiplied by post multiplied by S I minus A whole inverse B is equal to B transpose S I minus A inverse Q, then S I minus A whole inverse B. So, I multiplied by both sides this one. Then what we can do it, because this equation I pre-multiplied the left hand side and right hand side, I may pre-multiplied by this one and post multiplied by this one, that is what I have written it here. Then after that, after simplification of this one, we will be getting that one, that B transpose S I minus A whole inverse, see this one, if I multiplied by this, if I pre-multiply by this one and post multiplied by, you push it this inside. So, S I minus A inverse will be identity matrix. So, P B will be there, agree. So, P B will be there, agree. So, this will be a P B only plus, see that one, this multiplied by this. So, S I minus A whole inverse multiplied by S I minus A. So, that will be identity matrix. So, it will be B transpose P into S I minus A inverse B. So, B transpose P, P is a symmetric, is agree. So, B transpose P into S I minus A whole inverse B, agree. Then this multiplied by this one and post multiplied by this one. So, this we have to write as it is what we got it. So, this will be B transpose S I minus A whole inverse P B R inverse B transpose P into S I minus A inverse B is equal to right hand side as it is S I minus A whole inverse Q S I minus A inverse B. Okay. Let us call this is equation number 7. So, what I did it here, if you see, I am pre multiplied by post multiplied by that as I mentioned here, and then pushing this pre multiplied by part of this one pushing in this expression, and this is also pushing in the inside this bracket. Then we got it that one. Using K is equal to R inverse B transpose P, which we can write it R K is equal to B transpose P. Using this expression in 7 and adding both sides, adding to both sides R, we finally get what we will get it, what I use in this expression, whenever I will get B transpose P, I will use R K, or P B I will write K transpose R, K transpose R transpose, since R is a symmetric matrix, it is R only. So, we will get it this expression finally, that right hand side we will get it as it is, the right hand side of equation, right hand side of 7 we will get it B transpose S I minus A whole inverse Q S I minus A whole inverse B, agree, and left hand side of S of 7 we will get it the in place of this one I will write it B transpose S I minus A, and in place of B it is a K transpose R, then R K, this is will be into this, what is this one? This will be coming R K S I minus A whole inverse B, agree this. So, I will discuss the what is called next class, that what we have to, the remaining reduction we will do next class, agree. So, we will stop it now here.